Lesson 3 is the first of 3 lessons on algebra, and here again an introduction and hopefully mostly review. In the image is a part of a bluefin trevally, and you can see the spots on there, both blue spots and black spots. And the question there is how many spots are on the side of that trevally, and in algebra we use variables to represent an unknown quantity. I don't know how many spots are there, I haven't counted them. And so we might say, well, the number of spots right now, we say that equals x. We'd use a variable there to describe that, and that allows us to create a general algebraic expression that can have an infinite variety of particular applications. So spots on this bluefin trevally, spots on that bluefin trevally, and that one, and so on and so on and so on, an infinite number of different applications using one thing, a variable. So make sure you looked at your rules and definitions for this lesson, and those are always good to go back to and try to memorize. That's your foundation. Mathematics is deductive in nature, where we have a foundation that we build upon. Before reviewing, though, let's talk briefly about the origins of algebra and just that word. What does that mean? And in about 830 AD, an Islamic astronomer named Muhammad Musa al-Khwarizmi, he wrote the book Hisab al-Jabar, and that al-Jabar part we can kind of see in there, algebra. That book, I'm not going to try to pronounce the whole thing there, that just means the science of transposition and cancellation. So it's a book about working with mathematical equations. So like, for example, if you had this equation, 6x minus 5 equals 7. Applying al-Jabr, adding plus 5 to both sides, in other words, like that. And this should be very fundamental to you. You should know what I'm doing right now. 6x equals 12, you get that. And then applying all mukabala, that's dividing both sides by 6. That's what that means. We get x equals 2. Notice the variable x. Variable's not always x, it can be anything that we can use to say this is a general description that has particular applications. So books like Al-Jabr, they're important contributions from the Islamic culture. It's interesting that science did not progress in that culture. And Vishal Mangalwadi, he writes that Islam also believed in a compassionate God, like Christians do. They respect Jesus Christ as a prophet. So in other words, the Islamic religion does not reflect God's unity and diversity of the true God, where we have Father, Son, and Spirit are all one God. Also, that unity and diversity is described perfectly in the Trinity, and reflections of which we see everywhere, including in mathematics. But Islam, it failed to capitalize on its assets because it preferred to follow a military hero, Muhammad, in place of a self-sacrificing savior, Jesus Christ. And Mangalwadi, he goes on to say that the Islamic tradition, it could not liberate Muslims from the classical pursuit of power. So you can look at history. It reveals that normally science and math, they flourish in a service-oriented Christian culture that seeks to know more about Him. It stagnates in a self-centered culture obsessed with destroying others. So while algebra has its roots in Islamic cultures, it did not progress there, and there's reasons why. So over time, most of the words in Khwarizmi's title, they were dropped. I mean, it's kind of long to say all of that. Algebra is what we say today, and we normally think of algebra just as arithmetic that uses variables. That's really what it is, and we use those variables to represent the places of numbers in a more abstract way. So we'll look at true algebra, the working with equations part, beginning in lesson 4. And when we do our algebra here, our review, we're going to place a special emphasis on working with what I call calculus variables, things like delta x, where that's one symbol right there. It's not like a delta is its own symbol and we're saying delta times x, so make sure you understand that if you haven't seen that before. That's one symbol. X plus delta x, x plus h. Sometimes h is used instead of having to write a delta x. So in calculus, the focus is on how things change. not what they are, but how do they change over an instant in time or space. So we use symbols like delta x and h to represent small changes. So let's begin with part A on expanding and simplifying expressions here. Example 3.1, expand and simplify the following. So expanding, that involves applying the distributive property. If you don't remember what the distributive property is, take a look in your rules and definitions. Pause right now and review all of them if you need to. So look at A. Just take that x and multiply it by each term inside parentheses, and that's a fairly easy one. But first what we could do is inside parentheses, if there's like terms that we can add together, we normally like to do that. So do you see the 4 and the 1 there? That's a 5, right? So we could say x parentheses, add those together, 5 plus y. And so that's equal to x times 5, or 5x. Normally we put the number first if we're multiplying two things together and one of them is a number. When we're done with the multiplication, the product of that, we write the number first. 5x means 5 times x, right? And then x times y, plus in between because there's a plus right there. 5x plus xy. And we could have said yx. Associative property tells us that's okay. Order doesn't matter in multiplication. So standard form though is normally we do that in alphabetical order. It's not a big deal if you said yx though, but that's our expanded and simplified form. Moving on to B. Now we have two binomials there, so what we'll do is we'll take this x right here and multiply it by the 5 and then by the y, and then we'll do the same with the delta x, multiply it by the 5 and then by the y. Look inside parentheses, there's no like terms that we can add and simplify inside parentheses first, so we'll just begin our expansion. And so we'd have x times 5 is 5x plus x times y, kind of like what we had up above in A. We have that same part again, and now we add the delta x on. Delta x times 5 we can just say is 5 delta x, and then delta x times y we can just say that's delta x y. And if you want, for right now, just to remind yourself that it's not like a delta is one symbol and x is another, and so we're saying delta times x. Now all of that is together, so we could put that in parentheses as well if you want to. You don't have to, but if you want to do that, you can. And then C, let's do that one. Here we need to apply the power rule, and we could do that first. Z squared to the third power, 2 times 3 is 6, so that'd be a z to the 6. That's how we'd simplify that first before we expand. Look at the terms inside parentheses. Notice that we could cancel, we have an x squared over x, so that just becomes x over 1, or x. And then we have a y to the minus 2 over y to the minus 2. That's just 1, right? Anything, we have same over the same, that equals 1. So we can cancel that out, and it's understood that that just equals 1, and so we don't have to write a times 1 or anything. So now we have z to the 6th on the outside times 3b x over z plus 2h over z, common denominator there. And then think about z to the 6th over that common denominator of z. It would just be z to the 5th, right? We could actually just go ahead and cancel that as well right now. Cancel, cancel, and say that's z to the 5th. And so now we just have z to the 5th times 3b, so we could say that's 3b z to the 5th x plus 2h z to the 5th. And there we go. Let's do another problem thinking about binomial expansions here, and you've been doing those since Shormann Algebra 2 if you've been doing Shormann math for a while, and thinking of Pascal's triangle, think of the binomial theorem. Binomial theorem is in the rules, and so we'll just use that here. If you want to use Pascal's triangle, of course you're welcome to do that, but I'm just going to use the binomial theorem. And so in A, we want to find the third term. If we expanded that out, That's what we're thinking about here. If we tried to do x squared minus 4y times x squared minus 4y times x squared minus 4y and so on, and expand all of that out, simplify it, add like terms, what would the third term be? Now, that sounds like a really big pain to try to do all of that, but that's where the binomial theorem helps us. It shows us what, in that expanded form, what is the third term, just using a simple formula. And so for that, we would say 5 factorial, because it's to the 5th power, over 5 minus 3 plus 1 is 3 factorial, over 5 minus 3, that third term, 2 factorial, times the first term. What is the first term? It's x squared. To the 5 minus 3 plus 1 is 3 power. And then times the second term. What's the second term there? It's minus, got to put the sign in front of it too. It's minus 4y to the 5 minus 3 power squared. So if you don't understand where I'm getting all of these things from, you need to go look at the binomial theorem in your rules. I'm assuming that you're familiar with that, which you should be if you had a normal pre-calculus course before this. So let's simplify this, and we'd have a 5 factorial over 3 factorial, and think about that. That would just be like a 5, just do it over here to the side, 5 times 4 times 3 factorial over 3 factorial. Those cancel, and then times the 2 factorial will just be times 2. So we're really just doing 5 times 4 is 20 over 2 is 10, times x squared to the 3rd power, that's an x to the 6th power, and then times minus 4y times minus 4y, that'd be a plus 16 y squared. So now just think about the associative property. 10 times 16 is 160 x to the 6th y squared, and there we have it. B, find the 6th term of that binomial, x plus delta x to the 10th. If we expanded that out, what would the 6th term be? So here we're going to say 10 factorial over 10 minus 6 is 4 plus 1 is 5 factorial over 6 minus 1 is 5 factorial again. And then the first term is x to the 5th, parentheses, I'll say delta x to the 5th also. Do the math on 10 factorial over 5 factorial times 5 factorial. I'm not going to go through that again here. You should be able to figure that out on your calculator or however you want to do that and get 252 for that. And then x to the 5th, and then we'll leave that in parentheses, that delta x to the 5th power. And that's it. Problem 3, just simplifying these expressions here, and it says there, write all the variables in the numerator, all variables in the numerator. So it doesn't mean if there's a number, you don't necessarily have to write that in the numerator, but all the variables, put those in the numerator. Because there are different ways to simplify, especially a fractional form of something. So in A, one thing we should notice there is just the power raised to a power. So just be thinking about when you have a power raised to another power. So that radical sign, that means to the 1/3 power. So that's a good first step there, is just to say minus 8 x to the 9th to the 1/3 power, and then that to the 4th power. Now a lot of times when there's a radical sign like that, they're designed to simplify into just simple integer values, and so we think if it was a square root, we'd be thinking like what times what equals that number. Is there something I could simplify it easily? Well, it's a cube root, so we think what times what times what equals -8. There is something, right? -2. That would work for -2. So we could say -2, and then x to the 9th to the 1/3 power, just apply the power rule right there for your exponents. 9 times 1/3 is 3, right? It's x cubed. Minus 2x cubed, that to the 4th power. What is minus 2 to the 4th power? Well, you're multiplying a negative 2 4 times in a row, so it's going to make it positive, right? Because you're multiplying it an even number of times. And so that would be a 16. And then x to the 3 times 4 is x to the 12. So there's the simplified form. In B, we see bases of B and C. So you should remember the rule: similar bases multiplied together, you can just add the exponents. And so writing all the variables in the numerator, we could just go ahead and do that now. We could have a b to the x plus delta x. Move that b to the delta x up, and it would be a b to the minus delta x. And then we have the c cubed. Move the c to the minus y up, and you have c to the plus y. Similar bases multiplied together, you add the exponents. So if we add the exponents of the b terms together, we'd have an x plus delta x minus delta x would just be an x power. And then we'd have a c to the 3 plus y. So there's the simplified form. Moving on to part B, we'll do some factoring and canceling review of just fundamental algebraic factoring and canceling skills. And so just looking at part A there, factoring, we want to factor the greatest common factor out. And so we look at the numbers between 5 and 15. 5 is a common factor there. And then for variables, we look and see if they have the same variable, so they both have an a, and then we look at the lowest degree one to factor out. So they both have an a squared, so we just factor out a squared, and then they both have a b. There's a b cubed and a b to the 1. It's understood that's b to the 1, right? So we just factor out a b to the 1. And so then we'd have parentheses 1 minus 3b squared. So think about it. If we tried to expand that back out, it should get us back to what that original expression was. Expand it back out. 5a squared b times 1, that gives you 5a squared b. That's our first term, right? And then minus 5a squared b times 3b squared. That will equal 15a squared b cubed. So we did factor that correctly. B, a group of things, a bag of sand, a bag of rocks, a group of things inside parentheses, a group of spots on a fish, that can be thought of as one factor. So this is the same thing as this, right? They're both 2x plus delta x. That's one factor. We can factor that out. And therefore, we'd have 3a minus b parentheses 2x plus delta x. We factored out a 2x plus delta x. We're going to do a lot of other types of factoring as well here in part B, but let's do a factoring and canceling. Something way back from Algebra 1, maybe even before Algebra 1, depending on your course, that students just struggle with. They look at something like A and they go, oh, 2x plus delta x over delta x. Cancel those, answer's 2x. No, that's not right. So if you're still having trouble with problems like this, write down a key idea. The only thing you can cancel is factors. Do you see a common factor in the numerator and denominator? There actually isn't one. So what you could do to simplify this is just break it into two fractions. And we could have a 2x over delta x plus a delta x over delta x. And so that just equals 2x over delta x plus 1. So that'll be our simplified form there. B, do you see a common factor? Yes, a 3x. Factor that first. You can't just go like that and say the answer is minus 9xy. That doesn't work. So you have to factor a common factor and cancel that. 3x times 1 minus 3y over 3x. And that 3x on the bottom, that is a factor, right? It's understood that that's 3x times 1. We just don't write the times 1 part normally. Cancel the 3x's, and we're left with 1 minus 3y over 1, or just 1 minus 3y. Problem 6, factor the difference of two squares. So a key idea there is the difference of two squares. And so you're looking for like a x plus y times an x minus y kind of thing. A first plus second times a first minus second. That's how you factor a difference of two squares. So also we want to recognize and identify squared values there. And so for a, which is pretty easy, we just say x plus delta x times x minus delta x. And if you wanted to, you can expand that out and see that the x times delta x terms would cancel because you end up with opposites, equal and opposites. B, first let's identify what the first term, what we'd say that first term is. And we could just call that 2a. And the second term, we could call that 6b, because if we do f squared, first term squared, that's 4a squared, right? 2a times 2a. If we do the second term squared, 6b times 6b, that's 36b squared. So it's just first plus second, 2a plus 6b, times the first minus the second, 2a minus 6b. That's how we factor the difference of two squares. Problem 7, reviewing quadratic polynomials, so an x squared plus x plus a constant. Having that ax squared plus bx plus c format. So these will be designed to factor into integer binomials. So when a is 1, you can just think, well, what two factors when multiplied together equal c, and when added together equal b. And so for a, think about like a 12 and a 5. That would work, right? So that factors into x plus 12 times x plus 5. Because 12 times 5 is 60, 12 plus 5 is 17. Order doesn't matter on those binomials. You could have written x plus 5 times x plus 12, and that's fine also. B, a is 1 again, so we can think what two numbers multiplied together are 65 and added together are 8. How about a 13 and a negative 5? 13 times negative 5 is negative 65, and 13 plus a negative 5 is 8. So we'll have an x minus 5 and an x plus 13. See, look, a is not 1, a equals 3 on that. So when that happens, you can follow a similar procedure like we've been doing, but it just may take longer to find the correct binomials because you have more options to work with. 3, now since these are integers, it's going to be like a 3x and an x. It won't be like a negative 3x and a plus x or something like that. Usually that's not how these are. But it'll be, if it was a 6, then it could be like a 6x and an x, a 3x and a 2x. You have more options on one like that. But here we just can have a 3x and an x. So write those down first, either the 3x first or the x first. That doesn't matter. And then think about what you could put in the remaining spaces, that when you expand it back out, it'll give you 3x squared plus 5x plus 2. So a 2, we could think plus 1 and plus 2. That would work, having integer values in there. So expand that out. What do you get? You get a 3x squared plus 6x, and then multiply the 1 by the x plus 2, you get an x plus 2. So you end up with a 7x on the inside. So that's not right. So let's erase that. And it must be the other way around. So just like I did here, sometimes you have to do trial and error on these and play with them a little bit and see what works. And you can do that with mental math, or like what I just did, just write it down, expand it out on paper and check yourself. So this one, that would work if you expanded it back out. You'd have 3x squared plus 3x plus 2 times x is 2x plus 2. So this time we do get a 5x for that x coefficient, and so that one works, and so this is the correct factored form. Problem 8, factor the following. Just notice there you have sum and difference of 2 cubes. These are sum and difference of 2 cubes kind of problems, and there are formulas to factor those out. Look in your rules for those formulas if you don't remember how to do those, and apply those here. So we have a sum of 2 cubes, a cubed plus b cubed. That general formula is f cubed plus s cubed. First term plus second term cubed is equal to parentheses f plus s times f squared minus f s plus s squared. So we have a cubed plus b cubed is equal to, so just that first term f equals a, second term is just b. So we have a plus b times a squared minus a b plus b squared. And b, think about that. That one requires a little more thought to it. What's the first term on that one? Well, how about a 3 times an x times a y cubed? Because if you did that times itself again, that would get you 27x cubed y to the 9th. And then the second term is just delta x. So we'd have parentheses, kind of just keeping it in line with a, parentheses 3x y cubed plus delta x times first term squared. 3xy cubed times 3xy cubed is 9x squared y to the 6th minus first term times second term minus 3x y cubed, parentheses, I'll say delta x. And then last is b squared, second term squared. So kind of running out of room here, I'll just say delta x. And I don't say delta x squared, I need to say delta x parentheses, because it's delta x times delta x. So put those parentheses on it. C, maybe even a little more thought than A or B. Now think about C has an x squared, which I thought this was difference of 2 cubes that we were trying to do here. And that is, when you're doing practice sets, anything that references example 3.8, that's going to be a 2 cube type of problem. So here what we want to say is, what cubed gives us x squared? Well, x to the 2/3, right? X to the 2/3 times 3, the 3's would cancel, you get x squared. So the first term is x to the 2/3 power. The second term is a 2. This is a difference of 2 cubes here, so we have a 2y squared z. So since it's a difference of 2 cubes, we say f minus s times f squared plus fs plus second term squared. So using that as our template, now our first term is x to the 2/3 minus 2y squared z, parentheses, first term squared, x to the 2/3 times x to the 2/3, that'd be 2/3 plus 2/3 is 4/3, x to the 4/3, plus first term times the second term, and let's actually just move things around. We have that 2, the numerical coefficient. Let's put that first. 2x to the 2/3 y squared z, and then plus the second term squared, so that would be a 4y to the 4th z squared. Factoring things like this, you've done this for a long time now. It's not that it's necessarily a hard thing to do, but there are lots of terms there, right? There's lots of places to make a little careless mistake. So just be careful. That's why showing your work is a good idea on problems like this. That's why writing the template down that goes with the problem, use that formula up here, this one, what I'm talking about here, use that as a template to guide you and help you think about what to put where. Moving on to part C and synthetic division. Here we're thinking about higher degree, like higher than x squared polynomial functions. Sometimes it's difficult to determine whether they have simple integer binomials for factors, and that's where synthetic division and the factor theorem, look at your rules for that. Those come in handy. If you divide a polynomial by x minus some number c, and the remainder equals 0 when you do that, whether you do just regular polynomial division or synthetic division, then what that tells you is that x minus c is a factor. Synthetic division is just a simplified version of polynomial division. If you need to review that, refer to the lesson 26 of Shormann Pre-Calculus. A link to that is provided for you on the e-learning campus. So look at example 9 here, and we have a couple of polynomials there. Use synthetic division to determine, is x plus 1 a factor of either of those? And if it is, write the factored form out. So let's just start with A, and let's just use our synthetic division format. And I'm not going to talk about that much. I'm assuming you know mostly how to do that, and so this is a review. Use the review lessons if you're totally unfamiliar with this. So we put a minus 1. If x plus 1 is our factor we're trying to study, we put a minus 1 on the outside. If x plus 2 was the factor, we'd put a minus 2. If x minus 3 was the factor, we'd put a plus 3 right there. So now the next thing we do is we write down the coefficients of that polynomial. And so we have, it's understood there's a 1 there, and then a 5, and then a minus 17 and a minus 21. And so we also check to see if that's in descending order of the variable. X cubed, x to the second, x to the first. This is actually x to the 0, right? Because anything to the power of 0 equals 1, and it's understood there's a 1 there. So we don't normally write that there, but it is there. So now we just say a 1, a 5, looking at the coefficients, write those down. Minus 17, minus 21. Put our arithmetic bar there, and so the first thing we do is we bring down that first term, the positive 1. Multiply it by the negative 1. That's minus 1. Add those together. That's a 4. Multiply it by the negative 1. That's a negative 4. Add those together. That's a negative 21. Multiply by the negative 1. That's a positive 21. Add those together, we get a 0. So the remainder 0, that means x plus 1 is a factor. And so let's write that factored form here. X plus 1. Now how do we know what to write next? Well, we look at the results here. We look at these coefficients. And this is actually 1x squared. It's the coefficient for the x squared term in that factor, plus a 4x minus 21. So we write that up here. X squared plus 4x minus 21. And now just think about that real quick. Can you factor that easily, like into integer binomials? Yes, you could, because you have 7 and a negative 3. So x plus 1 times x plus 7 times x minus 3. That is our factored form. So let's look at B. Probably answer is going to be no, it's not a factor, just since we have two things here, A and B. Why would we do both of them the same way? But who knows? Let's go ahead and do it anyways. Good practice using synthetic division. Is x plus 1 a factor? Put a minus 1 here since x plus 1 is the factor we're studying. And now look at the descending order of variables, and we have all the variables there. If like the x squared term wasn't there, we'd need a placeholder 0. So we'd need like a 0 x squared if it wasn't there. But it is there, so we have a 1 plus, or not plus, but 11 goes next, 41 for the x coefficient, 55 for the x to the 0 coefficient, we could think of it as. Put our arithmetic bar, bring down the positive 1, multiply by the negative 1, get a minus 1, add, get 10, multiply by the negative 1, get a negative 10 there, add, we get 31, multiply by the negative 1, we get minus 31. Those aren't not going to add up to 0. We can put the remainder, it'd be 24, but we don't have to because you can tell that it's not going to add up to 0, so not a factor, we could say. So that's what we'd say for our answer on B. Our last part in lesson 3 is on logarithms, and like it says here, these won't be necessarily algebraic in nature in that most of what is here is variables. It's mostly numbers instead of letters, and it's a way to review the laws of logarithms and get you ready for future lessons as well, working with logarithms. So we think of that log base b of an argument n equals the exponent L. And then n is equal to base b to the L exponent, to the L power. So just rearranging those things like that. So that's what we'll do, is we're going to be going from here to here, rearranging and solving for what we need to. So in A, let's just rewrite that as x is equal to a base of 16 to the 1/4 power. Which there's different ways we could do that. We could think what times what times what times what. That would be a 2. We could also think, well, 16 is 2 to the 4th. That to the 1/4 power. Multiply those powers together and you get 2. And then for B, again, we can say 27 is equal to base b exponent 3. And these are designed to simplify into like a simple fraction or an integer value. So think 27, does that equal something cubed? Well, yeah, it does. It's 3 cubed, right? 3 cubed equals b cubed. So if 3 cubed equals b cubed, then b must equal 3. And that's it. And that is all for lesson 3.